spin is a fundamental property of particles. It's a very abstract thing, it's in the quantum mechanical realm. So we think about electrons and protons having this intrinsic spinning property, but you can't think of it as literally like the Earth spinning. This is something that's we really can't visualize, but we understand that particles have spin.
So right now we're trying to use spin, which is a property of electrons and protons. It turns out that depending on if an electron has a certain value of spin, or electron pairs have certain values of spin in the device, they behave differently.
The singlet is when two electrons, you promote a molecule and the two electrons are anti-parallel to each other. Now normally when it becomes a triplet, you just get one triplet for every singlet you started with. But in singlet fission, you take the singlet and you get two for the price of one. It's the ultimate, you get a free lunch, right? You get two particles produced. And so you get the possibility for every solar photon absorbed, you're going to make two electrons in the circuit. The way you measure spin dynamics is that you can use the fact that the triplet, this parallel pair of spins, has a longer lifetime, but it also has a different characteristic spectrum. So when we excite a molecule, we then take its spectrum. It's like we take a photograph of all the colors that it will absorb. And the triplet will absorb different colors than the singlet. And we can see the singlet turning into the triplet, and sometimes the triplet turning back into the singlet. So we actually see the spectrum of the molecule, the colors it will absorb, change as a function of time. So it's almost like making a movie. We don't see where things are as a function of time, but we see the colors as a function of time. And so you need a fast laser to excite and then unravel what's happening as a function of time. If we were to do this with just an ordinary fastest electronic camera, we wouldn't see it. We have to use very fast pulses of light and all optical measurements to see how they're evolving as time goes. So singlet fission is something we're very excited about as one of the real, I think, most exciting directions that's come out of the center, at least as far as organics so far. In a random way, we've actually shown that you can see singlet fission in these types of materials too. So we think that that's actually some new science that will enable new types of devices with higher efficiency.
It's important to spend some time thinking about why we're interested in singlet fission materials. We see these as a real solution to solving some limitations of conventional solar cells, as well as organic photovoltaics. So on the left is the solar spectrum, and on the right is the artificial system where we could imagine absorbing all of the colors of the spectrum. So we'd have different compounds absorbing blue, green, yellow, orange, and red light. When this happens, energy gradually migrates from the high energy absorbers to the low energy absorbers. And this is a wonderful way of collecting light, but it really limits what you can do in your solar cell, because whatever the lowest energy species is sets the voltage and properties you can get out of your solar cell. So this limits us in two ways. The first one is any photons that come in at less than the energy of that lowest energy species, here illustrated in red, are not used. They're not effectively utilized in your device. But the bigger problem is, as each of these steps is taken, as I go from the blue to green to yellow to orange to red, I lose energy in the form of heat. That ultimately limits the amount of energy I can get even from the visible part of the spectrum. And so the solution that we've come up with in terms of looking at singlet fission is, this is a different process that gets me from the high energy state to a low energy state. And so what I illustrate here is in the singlet fission process, I can take a singlet excited state, what I label here as S1, which combines with a singlet ground state to give me two triplets. In this way, I get a 2-for-1 split. I have a singlet excited state that is illustrated here in red that gives me two triplets. So in this case, I would absorb one photon and I would get two electrons out of my solar cell. So if I think about doing this in a mixture of materials, I've illustrated here that I can think about doing this in compound 1 and compound 2. Compound 1 would absorb the blue and green photons, engaging in singlet fission, creating an exciton at the same energy as my red compound that I'm showing here. So I'll get, for the green part of the spectrum illustrated, I'll get 2 electrons per photon, and in the red part I'll get 1 electron per photon. The two of these summed together actually improves our ultimate efficiencies from 31%, which we get in a normal cell, to 45% that we get in a singlet fission-based cell.
The next step is to basically check them out and see whether we can improve it or make them as efficient with the silicon solar cells.
So the next step in trying to get this to work is that we've shown this material to undergo singlet fission. We need to be able to dope in, put in other molecules that will absorb different colors of the light. So for the bluer parts of the spectrum, we'll get this 2-for-1 deal. But for the redder part of the spectrum, we need to have molecules that will absorb the red photons. We'll still only get 1 electron out for those. Those have less energy. The higher energy system, higher energy part of the spectrum, we're going to get 2-for-1 of singlet fission. So that's what we're working on right now.
So the next step is to basically assess the materials that we've been working on. We've been working on some model systems for about the last year or so that'll let us understand things like singlet fission. And now we want to go off and actually try to make new materials that are even better at doing what we've seen in kind of our model compounds.